Today is March 4th, Sunday, 2018, and this is Aaron Murakami with A&P Electronic Media and the Energy Science and Technology Conference, and we're honored to be able to have Jim Murray on the call today. For the last several years, pretty much the only conference calls we have done have been with Eric Dollard, and little by little, one of my goals is to start bringing on some of our other presenters. The upcoming conference in July is going to be July 5, 6, 7, 8, which is a 4-day conference instead of a 3-day conference, and it's basically the weekend following 4th of July, and that will be at the Eagles Lodge in Hayden, Idaho, which is, it's about 50-minute drive from the Spokane airport. Spokane, Washington is all the way on the east side of Washington State, opposite from Seattle. It's right by the Idaho border. And Jim has been kind enough to have presented at pretty much most of the conference, all the conferences except last year. He was in the middle of a move and was very busy, and so he wasn't able to make it. But Jim will be presenting at the upcoming conference, which we're excited to have him back. And his conference is going to be touching on, or probably actually going quite deep into some of the concepts relating to unity, because a lot of people are interested in, so-called free energy technologies. They're familiar with, the concept of over-unity, but most people don't really have a firm grip on what unity means. And would you kind of like to maybe cover a little bit of what your upcoming presentation is going to be about, Jim?
Well, it's a little bit difficult to get involved with that on the phone because, like I was telling you earlier today, there are a number of concepts involved which really, if you're not familiar with such things, are best elucidated by means of diagrams and equations. But essentially, there is a phenomenon which has been used since day one in the engineering of rotating components, most particularly motors and generators, which is known as a segregated load analysis. And essentially what that does is it allows you to subtract out the losses associated with every facet of the functioning of the device you're investigating, and to categorize them and separate them from the quantity of power that is literally providing you with the electrical or mechanical output. And it is the understanding of the details of this process and different types of efficiencies associated with that function which essentially gives rise to an understanding of the concept of unity. And it is only by having a good understanding of that particular concept that you eventually can make the leap to an understanding of over-unity. Most people just think that over-unity means that you have more power out than you do going in. The problem is that even though that basically is true, you have to understand the limitations and the boundary conditions under which a statement like that is meaningful. And in order to really set those boundaries, then you have to understand a great deal about the functionality and the losses and the various types of efficiencies involved in what you're measuring. And that's essentially what the presentation will be about.
Now, the segregated power analysis that you mentioned, is this built into a device that may be seen in some of the videos showing some of your old SERPs experiments, or maybe the transforming generator where it's kind of giving a power readout and it takes all that into account?
To my knowledge, I never did a segregated analysis, actually on, during the presentation or on the air. However, okay, I actually will be doing that this coming spring because it's essential to understand exactly how that works. And I might add that this is one of those interesting situations in which Tesla himself, in one of his lectures, goes into the subject matter very deeply. And I'm not sure that he uses the exact same lingo, because back then they did have different buzzwords than we do today. But essentially, when you do the final analysis, he was talking about the same things. And one of the things that he mentions, which is of paramount importance, is the fact that when he was investigating anything, whether it's a transformer, a Tesla coil, a generator, or a motor, he did his absolute best to bring the performance of that device as close to 100% efficiency as possible. And while that may sound like a very ambitious undertaking, especially for amateurs, there's really a lot of wisdom involved in that. Because I'm here to tell you that once you begin to understand the distinction between system efficiency and conversion efficiency, you will come to realize that you can actually have an over-unity device which does not show up at all simply because of the fact that you have buried the results in a lossy system. And right now that may not make any sense to you, but I've seen this 1,000 times in my own career, and I'm certain that the great master himself was aware of all of this, or he wouldn't have made the comment. So I think that there's a lot of clarification involved in bringing this type of thinking into the public awareness. And for those people who are seriously trying to understand the limitations of normal energy systems, it's totally mandatory to embrace and utilize these concepts if you want to have any kind of worthwhile success. Does that make sense to you, Aaron?
It does, and so it sounds like it's a critical part of anybody's foundation who's interested in this science. Now with this, is this going to require any kind of serious math skills for the average engineer to be able to utilize this information, or is it pretty straightforward once it's all the diagrams and the math is kind of laid out? Or what kind of experience does somebody need to be able to take advantage of this information in their own experiments?
Well, mostly, to be honest with you, once you understand the basics of it, it's mostly the same type of mathematics that would be used by an accountant, because another word for a segregated load analysis is an energy accounting. However, there's also some algebra involved, at least in deriving some of the expressions that are used. And ultimately, when you're dealing with specific waveforms, especially those that are complicated, you will have to embrace a little bit of calculus. But for the most part, the presentation doesn't require a great deal of mathematics on the receiving end. It's just a question of understanding the principles. And I think that I have the talent to get the idea across pretty rigorously and pretty thoroughly without overburdening the audience. I believe I can do that.
Okay. Now, about maybe 11, 12 years ago, I was doing a lot of experiments with pulsing a battery into some inductive resistors, and I was using a pretty sophisticated scope where I was looking at, the waveform like above the line, below the line, and I was exporting this out in a spreadsheet where it would give me the, the time and the voltage and everything on every single part of the wave, and kind of going through, kind of breaking it down into a spreadsheet like that. Is that kind of related to what you're mentioning?
Well, it depends. I really don't know exactly what you were doing with the information, but what this involves is the proper type of setup that you need, most particularly for rotating components, although you can use it in transformer systems and, high frequency stuff. if you have the right instrumentation to help you. After all, it is all about data acquisition.
Mm-hmm.
But the basic principle involved has to do with I forget what they called it originally, to be honest with you, but back around the days when DC motors were first evolving, and Tesla was probably still in school at the time, there was this big push to get the performance of motors as to be as high as possible and as reliable as possible, which is only natural once they realized what you could do with them. And in those days, they were actually calling the overall thrust of the effort the push for unity. And the reason, what they meant by that originally was that they wanted the power out to be as close to the power in as possible. And so, obviously, if you want to express that as a fraction, with the power out being in the numerator and the power in being in the denominator, if you have something that's 100% efficient, you're going to get a 1. And so that's where the basic thing comes from. But in order to derive that type of benefit, it was very essential to start to investigate all the reasons why the power output was less than the power input. And of course, you could sum that up and just say, well, it's all related to losses. Yeah, of course it's related to losses, but the question is, what losses, how does it work, and how do you minimize all those things? So that's why it took so long from the days when motors were just a curiosity to the point where they are now industrial workhorses. That's well over 100 years. And there was a lot of struggling on behalf of certain gifted individuals to do all of the legwork to make that happen. We have a tendency to take a lot of things for granted nowadays, assuming that it was always like that. And it isn't, or it wasn't. So I hope that adds a little understanding to your question.
Okay, yeah, absolutely. Now, for anybody listening, Jim is going to be at the upcoming conference here in about 4 months. And, we limit that to about 150 people. And that's because of the size of the venue, but it's small enough where people can have, spend some pretty quality time with a lot of the presenters. And so that's why we like to keep it at that size. Out of 150 seats, there's only about maybe 70 left, and we've only been accepting payments for about a month right now throughout February, and for 90 or about 85, 90 seats or something is taken already. And so that means we're going to be sold out probably a couple months ahead of the conference like usual. But if you want to come to the conference, go ahead and register, and you can get your tickets by going to energyscienceconference.com. And also, if you want to look at some of the past presentations of Jim Murray, we have emediapress.com. There's about 4, 5, maybe 6 presentations or so on there. There's Tesla's Hidden Discoveries. That was Jim's first presentation, which I believe might have been in 2012. I think that might have been the conference where you originally met Paul Babcock. And that kind of gave and that kind of gave an overview of a lot of your work. And then there's the Dynaflux alternator, which is a very interesting generator that seems very difficult to build. But in any case, several years ago, Jim did a presentation on the Dynaflux alternator that he invented, and I believe also gave some details which were not originally disclosed in the patent. And then he gave a presentation on the transforming generator, and And then one of the conferences, Jim did a co-presentation with Paul Babcock. I believe that was called The Secrets of Tesla's Power Amplification or Magnification, and that's dealing with the SERPs, the Switch Energy Resonant Power Supply. And there's a couple old demonstration videos on YouTube that you can find on that. And so right now, if you haven't had a chance to watch some of Jim's videos or the co-presentation with Paul, which is kind of on the SERPs concepts, that there's a coupon code which is JimPaul25, and for any of the presentations, once you check out in the shopping cart, there's a coupon code place where you can enter JimPaul25. It's all uppercase, and that'll take 25% off any of those presentations. And so, do you have any announcements, Jim, or should we just go ahead and just open up for questions?
Announcements, you mean pertaining to what I plan to present, or to what?
I guess just generally anything. If there's anything that you want to, anything else you want to share before we open up for questions?
To be honest with you, I can't think of anything because a lot of the stuff I'm doing right now I can't talk about anyway. But
sure,
I don't think there's anything else. But I'll tell you what, if I do think of something that's worthwhile, I'll just blurt it out like I usually do. Right now I can't think of anything.
Okay. Let's see now. Okay, so we can go ahead and open up for questions. Jean, since you're already unmuted, we have Jean Manning on the call. She's the author
Hi,
of...
Hi, Jean. How are you?
Hi, Jim. Fine. Just trying to understand some basics, and so far I don't feel like I do, but I'm going to keep hanging in there and listen to you this summer.
Yeah. Your presence will be well appreciated, and I'm sure we'll get a chance to chat as we usually do. So I'm looking forward to it.
Okay, well, I'll let the technical knowledgeable people ask the questions here.
Okay, and yeah, feel free to jump in anytime. Okay, so if you want to ask a question, go ahead and hit 5 star. Just hit 5 star, and that'll put a flag up by your phone number. And I'll go ahead and unmute you, and you can introduce yourself and ask your question. Santa Barbara? Yes, hi, Michael.
Long time no see.
Yeah, I've been trying to find you, Jim. I wanted to ask you, would you please reiterate the quadrature components of the electric wave?
Well, to be very honest with you, that's more in the providence of Eric Dollard. My way of analyzing stuff is a little bit different than his. And so rather than to, generate some confusion by interjecting my own thoughts on the subject, it ought to be presented, with a little bit of support information, whether it's my method or his method, and that would require a blackboard at least. But I mean, let's get your question a little bit more aligned, if you don't mind. What do you actually mean by what you asked me? Because there are a number of different ways that I can interpret that question. Go ahead.
When you and I were studying together over the phone some years back, you had provided me with the Einstein-de Haas paper, and you explained what that paper meant with your understanding of the quadrature components of the electric wave. And that's what I'm seeking out in a reiteration again of what you explained to me.
Well, okay, but that's actually a very different situation from the way I interpreted the question originally, so I'm glad that we cleared that up. The whole situation with the Einstein-de Haas debacle was actually involving the conclusions that were drawn early on in the investigation of the electrical phenomenon. And as you know, there's a natural tendency for physicists especially to look for universality in nature in all of its expressions. And so essentially in those days, what they were trying to do was to look for electrical phenomenon which essentially were mirroring or otherwise embodying well understood mechanical phenomena. And so this led to certain analogies being developed between the electrical expressions and the mechanical expressions for power, energy, and momentum, and all these various parameters. And when they had these expressions developed to the point where they felt that they were reliable, that then they started to pay attention to methods for making measurements which would either confirm or deny the theoretical relationships. And one of the first things that they were monkeying around with was inductance, because inductance is the key to everything from transformers and generators to motors and radio and heaven knows what else. And so they had come up with the idea that inductance was very similar to certain characteristics associated with inertia, more specifically with angular momentum. And so one of the things that was being looked into, and I think it was Maxwell who did it originally, because he was on the verge of developing his wave theories, which became the basis of electrodynamics years later. And he was looking for a device or a particle or something which would represent the carrier of energy in electrical systems. And I might add that this was before the discovery of the electron, and so there was a lot of ambiguity involved in exactly what constituted the flow of electrical power or electrical energy, depending on how you want to look at it. And so one of the things that they did was they built a series of windings and coils that were situated on rather large diameter hoops or armatures that they could spin at very high speeds and then bring to a sudden stop. And the idea of doing this was that they had ballistic galvanometers attached to the output of these devices, and they would accelerate them slowly up to very high speeds, like 15 or 20,000 RPM, and then slam a brake on, which would stop the rotation almost immediately, and then they would look for a pulse in a current pulse in the galvanometer, because obviously if there were charge carriers or some type of particles that were responsible for the current, they should have momentum characteristics. And just like when you drive a car into a brick wall at 90 miles an hour and you wind up out on the hood, they expected that there should be a surge of current associated with this type of device if it was stopped abruptly enough. And as far as I can recall, and I read this information back in the 60s or 70s, so my memory is not infallible, but as far as I can recall, the original people who investigated it didn't see anything in the results which would have convinced them that normal electrical phenomenon should be associated with any type of momentum. And so, as a result of that, Maxwell went on to develop his wave equations, focusing strictly on the basis of the fact that the energy was carried strictly by the electric and magnetic fields which surrounded the conductors, and other things like the internal current, the drift velocities, and all these other parameters which were known to exist were basically given a backseat position because they felt that their importance was almost negligible. So the well understood and well embraced Maxwellian theories eventually got distributed around the physics community and were accepted with open arms. But a few years later, after all the notoriety, Einstein repeated the experiments with this other physicist named de Haas, and they used much more sophisticated equipment, and they found out that not only were the inertial effects detectable, but so were gyroscopic effects and momentum effects and all sorts of other things that were never included in the original diagnostics. And the interesting thing, and this is the reason why I believe you and I were discussing it, Mike, is because of the fact that nobody ever went back to modify the original equations that had already been accepted internationally from Maxwell to include these other parameters and these other variables which are of significant value. They're not the type of thing you can ignore. And so there's plenty of room even today for experiments and for work along these lines which could lead to anomalous efficiencies if properly pursued. I hope that answers the question.
Yes. Thank you, Jim.
Yeah, no problem. And by the way, the reason you can't find me anymore is because I'm in Canada these days.
Yeah, Peter had provided me with a telephone number, and it went nowhere.
Well, I'm sorry for that. If you write me an email, I'll do my best to give you the right information. How's that?
Same email, Jim?
Yes, nothing has changed.
Okay, good.
Hello, this is Steve Okerlund.
Hi, Steve.
Hey, Aaron.
Oh, hey, Steve. Good.
Jim, it's a great honor to talk to you. I've followed your work over the years. As a researcher in this field, doing R&D for 35 years, I understand all the hard work and what a great contribution you've put out there for everybody. So, really nice to talk to you. I wondered if I was watching recently your transforming generator demo to a Japanese guy. I wonder if you got anywhere with these people or any of these kinds of things that look really promising, interest people that might take it to market. It seems like that's such a break on that all the time. Did you have any luck?
Well, I can bring you up to speed on that. There was a time in Oklahoma where I was based for about 15 years, where I was doing a lot of work on the transforming generator concept. And I might add at this point in time that the reason why I built the thing in the first place was to study the difference between EMF and voltage. I know that most people use the terms interchangeably, and I also know that, especially if you're using traditional Kirchhoff analysis, you can usually get away with doing that. but there are times, especially when you're trying to understand certain aspects of power generation theory, that just does not hold up.
Yeah,
And
experienced that in my
I'm sorry, I didn't hear you.
I said I've experienced that in my work as well. I have done some experiments in that area. I had another question that,
Well, wait a minute. I was going to answer the thing more thoroughly for you, unless
okay, go ahead. Sorry.
Well, so anyway, you asked about the Japanese situation. So yeah, they had shown a great deal of interest in that, and I actually built a machine just for them. Well, they paid for it, so in that respect, it was worthwhile. And what I was trying to capitalize on with that thing originally was the fact that I noticed that under certain situations, if you apply the load properly, and I'm going to put that in quotes properly because determining what that really means is the key to the whole thing. What happened is that the machine had a tendency to suddenly run away with itself. It would accelerate to an ungodly speed and blow all the breakers, and then you'd have to start all over again. And what we were looking to do was to isolate the reason for that and get it under control with a feedback system that would automatically cut back on the input power when that particular phenomenon manifested itself. But the complexities of the undertaking were pretty severe, and the budgets were into the millions of dollars to do this. And the long story short, they backed out of it after I explained what was required to reach that plateau of understanding. However, I was approached around that time by a very lovely young man, Dave Squires, I think was his name. Is that correct, Aaron? Is it Dave Squires?
Yeah, Dave Squires.
Yeah, and I really hit it off well with him. And he had developed a very keen understanding of certain types of software analysis. And he asked my permission if he could use his software as a means of exploring what I was doing with the transforming generator. And at that time, I was already focusing on other ideas, and I didn't see any problem with it because the patents were already issued wherever they were going to be issued, and the whole thing was in the public domain, more or less. And so I said, sure, go right ahead. Well, about 3-4 months later, he called me all excited. He said, listen, he said, I think I found a way of applying this very specific idea that you had to separate EMF from voltage into a slightly different arrangement which would allow for the construction of a 3-phase alternator that could outperform anything on the market because it would have essentially zero source impedance. And he asked my permission to go ahead and look into that. And I wasn't in a position to, you can only do so many things yourself. So I said, sure, go ahead, be my guest. And he developed that, and then at one of the other conferences, I actually got to meet him in person, along with Paul Babcock. And Paul took a great interest in that, and since they were neighbors, essentially, Paul picked up the ball and started to work with him in that regard. And interestingly enough, there was nobody, I don't think, in the U.S. at that time that was interested in putting a dime into the situation. But somebody from one of the Middle Eastern countries, and I honestly don't remember which one, said that they would like to develop that if it passed muster with some big university over there. And so they developed a great big presentation and presented it over there to these university authorities. And those people went bonkers over it. They really liked it. So I think that there was some very serious exchanges and some movement towards actually funding the development of a miniaturized three-phase version of the transforming generator for that purpose. But then, unfortunately, Dave passed away from cancer, and I don't know where the situation stands at the moment. So, yeah, there's lots of things that can still be done with that. You know, the idea as I left it was basically in its infancy. But there's lots of brilliant minds out there. And the name of the game here is to cross-pollinate as many other people as possible with these new concepts, because that's the only way that progress is really made. And people have to just get off their duffs and go to work. I started into this stuff when I was 19 years old. I'm 70 now. I never quit once. And it hasn't been a linear progression, I can tell you that. So if you're going to get anywhere, you just got to keep your nose to the grindstone. So I wish you the best of luck in all you're doing.
Well, thank you. I wondered if you could answer one more quick question. Something I'm working on right now. I gave up on the idea of all permanent magnet motors, self-running motors, a long time ago, but I played with something back in 2010 and demonstrated it to Nassim Harriman when I was working with him and his investor. I have it on video where I was able to show that I could mechanically commutate a permanent magnet stator in such a way that it uses a magnetic guide track to bias the flux path, which diverts it momentarily in sync with the rotor's position. The gradual redirecting of the circuit allows the flux to maintain a constant density and polarity while commutating at the appropriate rotor positions. And I have it animated, and it looks all perfect, but I just had to give up on it because of the funding issues, and I was working on other things. I just wondered if you think something like that is possible.
Well, what was your main objective in pursuing that, if you don't mind me asking?
Well, like you said earlier, the more complex your system is, the more chance you lose your over unity potential. So I wanted to find something really simple to work on, and this has very few parts. It's non-electromagnetic, commutated, and it's actually just quite simple, and just very little possibilities for losses. And so I'm looking for help to get that moving forward again. But I do have a demonstration.
Well, I'll tell you what to do. You take and get a hold of Aaron and send me an email through him, and put your contact information in there, and we'll talk about this further. And I'll tell you why.
Great,
because you picked up on something very interesting, whether you're even aware of it or not. There are actually two types of commutation anyway. One of them is the electrical commutation, which everybody who has ever run a DC motor at least has a superficial understanding of. But there's also a thing called positional commutation, and to my knowledge, the master of that phenomenon was Nikola Tesla himself. And so if you are approaching this from an intuitive point of view, which I kind of have the feeling you might be, then you may have stumbled on to something that I could possibly be a little helpful to you in. And I don't mind doing that when somebody is sincere and serious. So get a hold of me through
I appreciate
Aaron.
that. I appreciate that very much, because I know you're also very good with magnetic analysis, finite analysis, element analysis work, and that could be very helpful with this. Yeah, I'll get a hold of Aaron and I'll get in touch with you. Thank you.
All right. Well, good luck in the meantime, and thanks for a good question.
You too.
Okay. Thanks,
All right,
Steve.
sir. Take care.
Okay, yeah, you're unmuted. Go ahead and ask your question.
Hello, Jim. Can you hear me?
I can. Who's this?
Okay, my name is Jack Hanlon. I live in New Mexico, and I've very much enjoyed watching your videos, and I was disappointed that you didn't make it to the conference last year. That was my first time to come to the conference, and I was looking forward to seeing you. I'm just kind of starting out in this area, and I'm a retired engineer, and got started by some friends of mine, and we decided to try and build a quantum electronic generator called the QEG. I don't know if you're familiar with it or not. And so we've been working on it now for 3 years with about the same luck everybody's been having, I think. And we're about the best we can get is about 44% efficiency if we just measure the power out versus the power in. But one of the things that in working and learning about this field is that there seem to be a lot of people that claim over unity, and sometimes big numbers like 9, 10, even more. But it seems that very few people are looping their machines. And I guess my feeling is that it seems that it's possible to start machines and then have them generate enough electricity out that you can take some of the output in and replace the energy or the electrical input that it took to start the machine. And that was one of the things that interested me in the WITS video about the quantum electronic generator, and other videos there, which seem to be very few, where the people are really start the machine from, say, the wall plug and then unplug the machine and keep it running. And I don't know, in watching your videos, it's hard for me to tell whether the machines that you claim even large amounts of over unity output, whether you have looped any of these machines or attempted to loop them, or you know of other people who have looped machines. Is that... am I looking at this in a way that's reasonable?
Well, let's put it this way. I think that looping, if you want to use that term, should be left to the very last if it's going to be done at all. Because if there isn't sufficient gain involved, you can loop all day long, and all you're going to get is diminishing returns. So rather than complicate the issue by trying to do anything like that, I've spent my time specifically developing devices in which you could measure a very positive differential. And what I noticed was that in order to make reasonably good numbers of that sort, you are faced with the interesting task of re-examining the losses in very novel ways so that you can find methods for either circumventing their effects or minimizing their effects. And one of the biggest, of course, is the iron losses in any kind of relatively low-frequency machine. And that's where I tend to spend my time, is with, 60-cycle, basic power line frequencies. And so that's where I'm mostly developed any expertise that I may have. But more specifically to the question, I don't know of anybody that has successfully looped anything. If they're out there, that's great. They haven't shared any of that sort of thing with me. I have definitely seen situations where there's over unity in the true sense of the term, but as I tried to point out earlier in today's chat, when you start looking at the system efficiency involved, even if you have a healthy over unity number, if your basic losses are high enough, the effect can be drowned such that the overall worthwhile gain is essentially drowned, and you're not going to be able to loop anyway. So basically, I have concentrated on understanding what is the problem, or what problems prevent certain things from happening. And it's taken me a lot of years to come to an understanding of some of these things, and a lot of money spent. And I'm here to tell you one thing. The mathematics that's involved in anything that even remotely resembles success in this direction is almost overpowering. There's just so much to know and so little time to a given lifespan that it really makes you wonder how geniuses like Tesla managed to do so much in so few years. I'm very fortunate in the fact that I have the assistance of an unbelievable mathematician, and we also have, some pretty impressive computing power, because some of these things, solving the differential equations alone, if you were doing it by hand, you'd be lucky to do one a year. I mean, some of them are that involved, and thank God for the computing power that's at our disposal at this point. That's all I can say. So if you're serious about pursuing this stuff, just don't be overwhelmed by the math. It can get a little bit hard to cope with.
Mm-hmm. Well, it's not the math that scares me as much as the experimenting. I've done a fair bit of math in my career, but experimentally I haven't done nearly as much in the electrical area, and so I learned a lot of things. I don't know quite how to put it. I guess I know more than I understand. Maybe that's the way to put it.
Is your background mechanical or electrical?
No, my background is electrical, but most of my work was optical. So I've been through all the standard stuff, and but I spent most of my career working in optical engineering, and it wasn't until I retired that I thought this all looked like it was an interesting thing to do, and and surely it has been interesting to study this stuff and to try and build a machine and look at all the things on the web. There's just an enormous amount of information, really good information on the web and in different places that you can find, but it's interspersed with all kinds of things which you don't know whether to understand or not. And so to me, the proof of all this seems to be that if you can loop a machine or take away the input after you get the machine started, and the machine continues to run for a significant amount of time, that seems to get away from all of the arguments that people have that it's impossible to do this sort of thing. And so that's kind of where I see that it kind of falls short, in that not many people seem to show machines that do that, and if they have a machine that does that, they won't tell you how to do it. And So that's kind of where I'm coming from, and one of the things that I think would really help the field along is I know that there are roughly 100 QEGs out there, and there's no one that I know who has been able to get one of their machines to put out more than 50% and power out over power in, which I would guess that you would call system efficiency.
Yeah, that's correct.
And so if the community could get the quantum electronic generator to work, then I think right away you'd have 100 machines out there that would be producing something that people could believe. And I think it would really help the field along. But, of course, at this point, nobody knows how to do that. So I wonder maybe at the conference.
You're probably correct, Steve. And let me throw a word of caution out to you.
Or Jack.
Yeah. Mm-hmm.
The notion of looping, as you like to call it, a generator, or an over-unity generator, if you want to use that term specifically, with its own drive motor, may or may not be what people think it should be. And the reason I say that is because a motor's ability to draw is specifically related to its internal workings in terms of the impedance it needs and the voltage and current that it needs and what have you to keep running. And the other problem is that the generator is kind of the reverse of that. And so, like, even if you got a situation well matched, you may very well find that you get diminishing returns anyway. And the reason I say that is because the tendency would be to imitate a flywheel, because that's really all you're going to have. It doesn't make any difference how much power the generator is capable of producing, because the motor is only going to pull what it needs to run. And that's where the idea of looping falls short, in my estimation. That's the reason why I reserve that concern for the last, as opposed to something to do early on, because otherwise you could very well be chasing your own tail, so to speak. I don't know if you understand what I mean about that.
Well, yes, I do. I mean, there's no need to try and loop a machine that only has 50% of out of what you put in. There's no need to do that. But if you have 7 or 8 times more out than in, I would think that the golden egg is to take some of the output and replace the input, and then you have a self-standing machine. And I just,
yeah, but here's the rub with that. You see that what you don't seem to realize is that first of all, the mathematics that describes a motor and a generator are actually the same. And so all motors are already generators, and all generators are already motors. So even if you have a device that's over unity, so to speak, if you're running an ordinary motor with it, the motor is only going to pull what it needs to pull to behave as a motor. It's not going to take more than it needs from the line. And the generator is only going to put out what you're demanding from it. So these two features actually operate at cross purposes to one another if you really understand what's happening. And actually, that's an area that I intend to touch upon this summer. Not so much from the standpoint of worrying about looping 2 machines, but because it's an essential thing to understand if you're interested in doing this work. And it's very difficult to get into it in detail without some kind of support, because I have to spend hours painting mental images for you to follow. But I just doubt that that particular solution is worthy of pursuit all by itself. Let's put it that way. I understand where you want to go, and I think that that's ultimately a great idea, but I think that you're not going to get there without going through a whole bunch of intermediate steps, and making use of those steps is going to depend entirely upon how well you understand the overall situation, and not just labor on the assumption that looping is something that you can do easily.
Well, no, I don't think it's easy.
No, it's not.
Yeah. But, I mean, even if you look back at the conference, even, you know, Babcock's machine, it surely seems that there's lots more energy available at the output than he has at the input. I mean, you see the shaft rotating, and he measures the horsepower out and tells you what the power in is. I guess, you know, there seems to be a little bit of problem that I see too, that it seems like you have to get some energy into the machine, into the system, from some external source. And I know Aaron is trying to show these sorts of things, and other people have talked about these things, which is trying to bring in radiant energy through by releasing some of the energy from what people would call vacuum energy by sparking a spark gap at a certain time in the cycle, rotor cycle. But I don't know if that's the key, or if it's really a reorganization of classical ideas. It seems that you and Babcock seem to be saying that a lot of this is just conventional engineering looked at and utilized in a different way. And then there seems to be a group of people that say, if you're going to get these machines to run at high over efficiency, that you're going to have to tap into this mysterious vacuum energy or something like that, which I guess that I would say I think the physics community would say it really exists, but nobody's been able to tap significant amounts of power out of it in a consistent way and advertise that they've done so and been so. Can you shed any light on that any more than you already have?
Well, unfortunately, I think there are many answers. There isn't just one answer. I believe, from what I've seen in the last 50 years of my own work, that you certainly have variations of so-called conventional theory which give anomalous results. You also, for sure, have non-traditional approaches to the energy enigma, which have also borne results. And that goes back to, you know, Tesla and Hubbard and all kinds of other guys that were messing around with things in those days, Stubblefield, the list goes on and on and on.
Mm-hmm.
But also you've got the hybridization of systems where you have something classical intermingling with something of a non-classical nature. And the problem is that there are so many variables, and they all present unique problems in intermarrying them. And so after spending a lot of years just seeing what was out there and experimenting on my own, I came to the conclusion that the best way to optimize my time was to concentrate on those things which I understood intuitively the best. And that became an all-consuming effort on my part, because even by restricting my own activities to, let's say, 3 or 4 different embodiments, the complexities are overwhelming. And the amount of money that's required seems to be endless. And, and I'm sure that there are plenty of people out there far more brilliant than I am who have even more amazing theories by the tail, so to speak. And they're investigating a whole slew of different things, even if it's privately or in black projects or wherever it's going on. And so I can only answer the question by saying that I think that there are many, many ways to skin this cat. I'm only familiar with 4 or 5 of them. And those are the only areas where I can truly talk with a combination of experience and a certain amount of achievement. As to the other things, God only knows what's really possible. That's part of the problem with all of this, is that some of it is subjective as well as objective. And since we all have different fractions of the divine mind to work with, our perceptions of reality are very, very different from one another. And usually they're quite subjective, at least until they're objectified by somebody who actually achieves something. So it makes for a very complicated undertaking, regardless of which path you choose.
Well, that's really true, and it's a fascinating field to work in, and thank you for all the stuff that you've done, and I look forward to meeting you at the conference this summer.
Well, I'll look forward to it too, and good luck with what you're doing, and when we do get together, maybe we can talk about it in a little bit more detail.
That would be great. Thank you very much.
Thanks.
You too.
You're
Thanks,
welcome,
Aaron.
Jack. Go ahead and introduce yourself, where you're from, and go ahead and ask your question.
Yes, this is Ron Soren. I'm in Boise, Idaho. I've been to the conferences for the last couple of years.
Hi, Ron.
And I've listened to Jim and Paul and several others. But the interesting thing I found is what Jim mentioned, the system versus conversion efficiency that he's going to talk about. Hello?
Yes. Yeah, I'm here. I'm listening.
Okay.
So what's your question?
Well, I've been playing with call it a high voltage transformer for years. I built a little test instrument that boosted line voltage, 120 volts, up to about 400 volts, 450 volts RMS for testing coils, for testing small engines. And it would act as a high voltage ohm meter. And there's some efficiency problems with those cores. I was wondering if what you're going to cover is the efficiencies of various materials as far as transforming characteristics.
Well, there's so many materials that I'm sure that each of them have their own loss characteristics, and naturally I'm not familiar with all of those. However, speaking in generalities, you basically hit the nail on the head. It's very important to understand the difference between conversion efficiency and system efficiency. And for the most part, conversion efficiency has been thrown in the junk heap because the assumption is automatically made that the conversion efficiency of anything worthwhile is limited to 100%. And if that were true, then there's no point in struggling with any research any further, because it automatically would imply that you're never going to get anywhere.
Well, you won't get anything over unity. Is that correct?
Well, that's the whole point. If you didn't have something over unity, then why would you want to proceed? You have to jump in the boat with everybody else and say everything that has been done, I mean, anything that can be done already has been done. But I happen to know that that's not the case, and I can demonstrate it. So the point is, it becomes very, very vital, in my opinion, if you want to pursue this type of thing, to understand completely what is meant by both of those terms, what the limitations are as they are presently understood, and how to effectively exceed those limitations with actual working devices.
With working
And
materials.
so,
Yeah. Okay, so when you talk about, is there a way to separate out system versus conversion? In other words,
absolutely.
That's what you want to be able to do.
The whole point.
Okay. All right. Do you have a way to measure that, though? I mean, haven't you said
yes,
that
you can measure it. You can measure it, but the point is, it's not done with one measurement, and that's the reason I said at the beginning of this talk that it requires a pretty good understanding of what a segregated load analysis is all about, and how to perform that intelligently, and then what to do with the data. Okay. So those are the types of things that I would like to present and talk about this summer, but to do it on the phone is really kind of difficult, because even if I wanted to get into it, you would have more questions than I could possibly answer in the amount of time, because it's just not the type of thing that lends itself easily to mental pictures, and I'm only so good at generating graphic images with verbal descriptions. You see what I mean?
Mm-hmm. Yes, Jim. I understand, but I'm just trying to get an idea for what I was doing with these little transformer cores that I've got hundreds of them sitting in a box. I've got all these little E's and I's, and I've got
are they ferrite?
They're actually a soft iron. I don't know the hysteresis characteristic of them, but they're a very inexpensive core material. They're iron, but they're very soft iron, and I probably got about 50 pounds of them or more. But I don't use them anymore.
Have you measured the permeability of them?
No, and I'm not certain how to do that. My background is mechanical engineering. I worked with magnetics, weird stuff like vanadium permandor, which is a cobalt iron mixture, for horseshoe magnets on impact printers. I dealt with that because of the characteristics that it had with being heat treated a certain way. It would become very dead soft. In other words, magnetically soft, and had virtually no hysteresis volume in the curve. But the material I have, it doesn't show any residual magnetism when I magnetize it and play with it. But it's just a cheap, inexpensive iron core material. Thickness is about 10,000ths of an inch. Very soft. I mean, bend it, you can't stack them together flat anymore. So, but it works for these little transformers, but I don't know the efficiency of it. And I'd like to be able to measure it, like find out if I put 120 volts in, should I be getting, what value should I be getting out? I have a book that tells about transformer design, but there's very simple mathematics. It's using basically algebra. There's no differential equations, no analytical analysis of what can occur with that material or with a transformer material. And the company that I buy them from says, "Oh, you've got the cheap stuff. It's low."
Well,
low frequency.
first of all, let me clue you into one thing. Are you familiar with, or do you have any watt measuring equipment?
Hey, what was it? You called it
Watt
measuring?
Do you have any watt measuring equipment?
Oh,
in other words,
no, I don't.
Watt,
I don't have a watt meter. I have voltmeters and ammeters, and I do have a four function or a four probe oscilloscope, but they don't give me.
If you don't have a watt meter, you're going to have problems doing what you want to do, because you can't get an efficiency measurement by just measuring voltage. Sure, you can get a voltage transfer efficiency, but that's not the same thing as a power transfer efficiency. As a matter of fact, they're as different as night and day.
Right.
You have to put a known load on there. You have to go through all of the impedance measurement characteristics. You have to know the source impedance, the load impedance, the transfer characteristics for everything. And you have to be able to measure the wattage going in and the wattage coming out. And, the other problem is that as soon as you get into this, you automatically open the Pandora's box, because there's watt meters and then there's watt meters. You got average responding watt meters, and then you got true RMS watt meters, and then you got a whole host of garbage in between where people just throw stuff together so they can make a few bucks at your expense. The best instruments that I know of are Yokogawa series watt meters, and they are usually affordable. You can get an electronic version. What's that?
What was the name again?
Yokogawa. It's a Japanese.
instrument. Yokogawa. Okay.
No, Yoko. Yoko with a Y.
Y-O. Okay.
Yokogawa. And they have accuracies of plus or minus 0.1%, and you're going to need a minimum of 2 of those, and they're going to run you about $1,250 a piece. But you might be able to get them cheaper off of the internet or off of eBay, as long as you can get one that's in good condition. And I would start off, even if you do buy a couple of them, the first thing you should do is have them professionally calibrated.
Sure.
Otherwise, you're not going to know where you're at.
Okay. Well, see, that would help to see what type of thing I'm getting off of these little transformers, but I just want to play with them right now to see what I can get for a magnetic field impulse off of them, because they're not, they have to be machined, they have to be modified, but I have no way of knowing what the core efficiency is of the material. I can call the manufacturer of the material and say, how do these run, but it's all frequency dependent. And
well, not only that, but if they're a really reliable company, whoever they are, you can request the BH curve to go along with their with the particular steel or iron that they are giving you. And once you have the BH curve, then you at least have something to work with. The other thing you can do is you can establish your own BH curve once you wind one of these things. You can put together some and use a sample of that material for determining your own excitation curve. But all of that takes not only a lot of work, but a lot of experience, because it's not one of those things where you go and read a book about it and then you go and do it and you have positive results the very first time. There's a knack to all of that stuff. It's like playing hockey or basketball. It's one thing to throw the ball around or bat the puck around, but it's another thing altogether when you finally reach the point where you develop a feel for what you're doing. And nobody can teach you feel. It's absolutely impossible. You have to develop it on your own.
Okay. Well, you're going to cover this stuff I mean, at the conference, I'm very, very interested because it would be.
Well, you're certainly welcome to attend, and I'll do my best to design this presentation so that it targets folks like yourself that have a real interest in understanding this material.
I'm trying to figure out how I can modify this material or do something with it that'll be fun. So I appreciate the help and the phone conversation. It was great. So,
all right. Well, I'm glad I could be helpful to you.
Okay.
You bet. Take care.
See you then. Bye.
Okay. Thanks, Ron. Okay, well, we're going on 2:20 right now, so I just want to remind everybody that, Jim will be at the conference. Over half the seats are already sold out, and so you can register and get your tickets at EnergyScienceConference.com. And also, before coming to the conference, if you're coming, it would be a good idea to watch some of Jim's other presentations, so you can kind of get a get a feel for some of his background and experience and what you might expect at the conference. And at emediapress.com, that's where you can find some of, actually all of Jim's presentations that he gave at the conference, in addition to the presentation he co-presented with Paul Babcock, The Secrets of Tesla's Power Amplification. And right now we have the 25% off, so when you check out the shopping cart, you can just enter Jim Paul 25. That's all capital, and that'll get you 25% off. And let's see, if nobody else has a question, I'll give a few seconds, see if anybody wants to hit 5-star. Otherwise, we'll go ahead and wrap it up, and we'll see you all at the conference. And if you're up to it, Jim, I'd love to do another call like this with you sometime.
Oh, yeah, I can fit these in, especially on weekends without too much difficulty. Sunday afternoon like this is fine for me. Yeah, I'll leave that up to you as to when you want to try to squeeze it in. Just let me know.
Okay. Okay, well, Jim...
probably should wrap it up, eh?
Yeah, we can go ahead and wrap it up. It's 2:30 right now, and so hope to see you all at the conference. And Jim, thank you so much for your time and for being willing to take some time out of your busy schedule to be on the phone with us today, and hope to do it again sometime.
Not a problem. I'll be here when you need me.
Okay, thanks, Jim, and thanks everybody for being on the call. Take care, everybody. Have a good week.
Yeah, thanks.
All right.
Bye.
Afternoon. Bye-bye.
Bye-bye. Thank you.